that philosophical viewpoint in the Spikes book versus, I guess, the dynamical systems view.
Right. That's the stuff I haven't actually put in slides, but it'll come up, I think. So welcome, everyone. And it's very cool that people have been attending for 3 months now. It's pretty awesome. So I think that the stuff that we laid out in the very first session to do with dynamical systems and Strogatz, we've more or less covered. We could talk about some of the chaos theory stuff in more detail, but I was partly inspired to do this by a Twitter conversation involving Mac and someone in London who he posted sort of one of those jokey tweets saying that I've gone through stages of information theory where I don't know what it is. I'm starting to learn about it. Well, this is obvious. And then one stage was, this is some esoteric weird stuff. So it's like, I was like, yeah, I think I'm at that stage 4 and I'm hoping there are more stages, was my response. And then Max said, I would love to talk about this. And I was like, yeah, why not? Because it's very much relevant to neuroscience. And in a way, it's a nice contrast with dynamical systems. And it helps you kind of see dynamical systems from another perspective.
Yeah, I think you skipped a stage in there, Johan, which is that information theory explains everything.
Of course. All right, so let's dive in. So before we get to information, I wanted to just talk about invariance or symmetry, which is something that if you hang out with us CNS people, me, Himanshu, Karthik, and gang, we always use the term invariance or symmetry, typically invariance. And if you haven't read my essay and you haven't looked into the math of this stuff, I almost think you should write down your sort of pre-mathematical notion of symmetry on a piece of paper right now. Because in my experience, whatever pre-mathematical idea of symmetry and invariance I have no recollection of. Because it's such a simple, elegant way of thinking that it basically replaces whatever you thought before, if you had a theory of symmetry before thinking about it this way. We all have some intuition about symmetry, which often involves balance, and typically left-right balance or bilateral symmetry. I like to always start with the etymology. It involves the same or together measure, so things that are measured that go together, not too surprising. And the way that I'm talking about this is basically inspired by Joe Rosen, who's written several books, all of which seem to have the same content, but he basically talks about symmetry as it's used in physics, and starts with some group theory, which is really the mathematical field where you really kind of see symmetry for in kind of its native place. So he talks about this in a wide way, and so we just dive in. Symmetry is immunity to a possible change. A lot of information packed into the notion of a possible change.
Johan, did you have slides that you wanted to share your screen, or
am I not sharing? Shoot. I thought I was sharing. I was going through the slideshow.
Yeah, that is what it looked like.
Okay. Yeah. So, well, this we already talked about, and now you see it, right? Yeah. Okay. So, symmetry is immunity to a possible change. There's a lot packed into that idea, and so here's some examples of some changes you could do to some triangles. And every symmetry implies an underlying asymmetry. This is a very simple idea that's like sort of so under the radar that it might not initially strike you why it's useful or important. Just looking at the examples that I've given you, can you tell me what might be the underlying asymmetry that I might be thinking about? Let's pick the equilateral triangle. And the possible change is, let's say, rotation by 120 degrees. The triangle looks the same after rotating by 120 degrees. So when I say every symmetry implies an underlying asymmetry, what does that mean? Would anyone like to?
The person or the paper that is staying the same?
Well, it isn't staying the same.
Right.
In order to measure something, you need a measuring device, and the measuring device has to change while the thing that you're measuring, it could change or maybe not change. So your protractor or whatever it is you're using to measure angles does have to change when the transformation to the triangle occurs. And even though this is just a sort of natural consequence of being able to measure something, it has implications for what you can say in a scientific way about anything. Because you can always ask, well, if I'm attributing a property to something, how do I know what asymmetry allowed me to catch this particular property? And interestingly, at least in this book, he says an asymmetry does not necessarily imply a corresponding symmetry, which when I wrote that essay, I was like, yeah, sure. Just because something is varying doesn't mean I necessarily have an invariant quantity. But and just bookmark, I wrote, do you agree? Because there's maybe a slightly sneaky or metaphysical way of thinking that might make you question that. We can come back to that later. It's just a little mischief to amuse myself, but maybe we can come
just to add one more thing.
Yeah.
Another way I think of asymmetry in the context of the rotation of the triangle by 120 degrees is if you number the vertices, then after rotating by 120, the triangle you end up with is, if you go by the numbering, it's a different triangle. But so.
Yeah. And when you're doing
Is
something,
it just another way of saying that to have a non-trivial symmetry, your transformation has to actually do something. It's
right.
not the same as like a change of coordinates. You actually have to move stuff around.
Exactly. Yeah. That's a good point. So actually, so I always like to imagine like a thought experiment floating in sort of a black void of space, and there's like a seemingly spherical object in front of me, and I have no measuring devices or anything. Can I know that I have circumnavigated this object? I can't make any marks on it, and I don't have a measuring tape or anything. I think the answer is no, because there's no features to tell you that you've successfully returned to where you were before. That's another way of thinking about the necessary asymmetry. So a lot of you will have heard of M.E. Noether. And so a lot of the time when people talk about symmetry, they specifically talk about how powerful it is in physics. This theorem that she's a mathematician, not a physicist, and apparently she wasn't that interested in physics, but she did something which revolutionized how physicists go about what they do. So you don't really have to know all the technicalities here, but basically a particular class of symmetries of this quantity called the action has a corresponding conservation law. A quantity is conserved. And here are 3 examples of the kinds of conservations that fall out of this. They were all known before, but she basically showed a new way of arriving at this, at these conserved laws. So translation in space corresponds to linear momentum. If you have a system that looks the same as it translates in some more, in a sense, then its linear momentum is conserved. If the system looks the same at a certain amount of time later, time translation or time evolution, then you have conservation of mass energy, which is a very nice way of understanding the link between time and energy. When you look at something, if it seems to be all the same, look the same and moving the same, then you'd think, well, it's conserving energy in some sense. And for rotation, you have angular momentum. So there are other quantities that physicists started to hunt for once they kind of understood this. So you could kind of flip things around. So instead of empirically testing things and hoping for a conservation law, you could instead look at the symmetries of a phenomenon and find a useful or measurable conserved quantity. So maybe this is an exaggeration, but physicists definitely started hunting for symmetries and symmetry breaking, particularly in particle physics, but elsewhere also. And Ryan can definitely talk about that a lot, especially symmetry breaking, which is so it's never the case that in the symmetry framework we're only interested in the symmetry. The violations are equally interesting in some sense. So yeah, there's just, you check out this editorial in Nature. She's still maybe not as appreciated as she ought to be in the wider public, so always good to bring her up in conversations. But for the purpose of what we're doing, we want to say that symmetry is not just this niche topic. If this is not intuitive for any particular phenomenon that you describe as a pattern, then you can sort of reframe what you're talking about in terms of pattern X is invariant with respect to some transformation Y, and then try and identify what that is. Sometimes it takes some work and sometimes it's unknown, but it's a nice way of reframing something that you've recognized as a pattern. So we can actually, test this out. In the case of a phylogenetic tree, what are some invariants or symmetries that you might think about? They don't have to be exact. They could be, and they typically are approximate. So would anyone like to talk about a symmetry of vertebrates or something like that?
Does it just mean what they have in common in this case? Like they all have a vertebra. That's, if different animals have the same thing, so that's invariant. So that's symmetry. Even though they're a different animal, so that's changed. The backbone is still there, so that's invariant.
And that could be a pretty powerful way of thinking. And evolutionary biologists will talk about homology, where you actually look through the family tree and you can make analogies not just between the overall organism, but between parts of the organism. So that's a kind of symmetry too. This is one of the most beautiful and elegant codifications of several symmetries. Again, would anyone like to name a transformation with respect to which something is invariant? Oh.
This one is awesome because if you study the hydrogen atom in your quantum mechanics class, you learn how to draw this table, when you more or less get it right by just thinking about how the electron orbitals transform under rotations.
Yep.
So like your 1s, 2s, 2p, 3d, and so on. Those are all different symmetry classes to organize this table.
But even like before orbitals were discovered, Mendeleev was basically establishing symmetry. So there are properties that are similar as you go down a column or across in a row. And which is why this two-dimensional structure really does a lot. And in a sense, it helped chemists think about what was happening and understand the valence shell, for instance, as something that conveys that these common properties. And closer to home in our world of dynamical systems, there are various sorts of invariants, which we may not have always pointed out that that's an invariant. But so for instance, here, these multiple thin lines, what are they capturing? An invariance with respect to what? Or what is invariant?
The differing initial conditions end up in the same place. So the same place is consistent among all of them.
Right. So that's true of limit cycles and attractors, these attracting sets. And you can get with the chaotic attractors, strange attractors, you'll have maybe a more probabilistic thing where a region tends to be attracted. So wherever you start, so it's invariant with respect to all these initial conditions. And there are other, we talked about normal forms and things like that. So it's like when you zoom in on a fixed point and then you linearize it, you'll get some kind of generic property that's invariant to the specifics of the rest of the system sometimes. So sometimes you need some transformation and it may be approximate. But the nice thing about symmetry is that it's not a all or none kind of thing. You can quantify it and have approximate symmetry. So one thing I like about Rosen, I think it's just in the first chapter, that he says science itself is a kind of symmetry. There are specific invariants that scientists are seeking. We need reproducibility of results of phenomena. We want predictability and reduction. Now, I've often said that I'm against reductionism, but that's different from reduction as simplification. Scientists do want that. We want some way of making a phenomenon amenable to understanding and control. And that Rosen likes to talk about it as a set of, he lists several, but there are two that are easily recognized. The reduction of observer versus observed. You want phenomena that are observer invariant. So if I swap out somebody in the telescope, they should more or less find the same results once they've followed the protocol. And then you have system versus environment context invariance. Now you might think, no, but aren't we interested in highly context-specific phenomena? Yes, but if they were so completely tied to the context that every time you change something, everything else changes, we would not be able to study it. So we're always trying to find an appropriate boundary where a phenomenon shows up as somewhat invariant. So that might involve, changing what we think of as the natural boundary that we were interested in. But, and this can kind of point you towards thoughts like, can science study phenomena that have no repeatable aspects? In some sense, something completely unrepeatable is imaginable, or at least it doesn't necessarily invade your sense of possibility. But from the perspective of symmetry, it's hard to say what one could do with such a thing. And he actually uses this idea to poke a little fun at cosmology, because if the universe, or if you like the multiverse, whatever it is that is the sum total of all things, is a one-off, event considered as a whole, then there's a limited sense in which you can say anything about it, because there's no higher asymmetry with respect to make claims. I'm sure a lot of people would have a problem with that.
Well, what about like the dinosaurs' extinction?
Interesting. I think that it's put together from things that are repeatable, like impacts, and also knowing what, like in the lab, you could test the way impact works on smaller things and models and computer models. So this is interesting.
Extinction is repeatable.
That's what I would think. Yeah, it's
also.
Yeah,
and it has happened multiple times.
Historiographic type science, like history itself, as well as cosmology. They're made of repeatable experiments, but then you have to piece together the experiments to tell a story.
Right, exactly. So when I said no repeatable aspects, I was giving myself some wiggle room now, because it's like any feature vector, right? Your feature vector will have a bunch of different things, some of which recur. Maybe there's one thing like your time index that it's just happened only once. But as long as you can decompose it into some things that recur, you have a way of at least putting a narrative together. I mean, that's a really good example.
Well, who's that? Sorry.
I like that example.
In general, with with cosmology or evolution, they're broadly in the field of what you can call as natural history. Natural history is not just about saying that there are unique events, right? At some level there is a taxonomy to it. The fact that they are to begin with, these are taxonomical fields before we had principles of evolution or whatever. Taxonomy is a form of symmetry, without which there is no classification possible. So even at that level, natural history is a symmetry, a field of symmetry, and not necessarily just. So maybe we should slightly modify that idea about like the repeatability aspect here. It's something else, not really about repeatability necessarily. We could have things that might
kind of. But it kind of is, or like in the sense of the dinosaur extinction, like that event is invariant to, let's say, a lot of little things that were happening on Earth. And if you take that to the extreme, there's some sort of sort of a distilled aspect of that event, like there's an asteroid or whatever, and that distilled aspect you can capture in like some model, and it has some kind of events that will consequently occur because of it. And due to this fact, we can look at or find certain evidence and then show that it would come out of some model that we would build. So
I like this a lot, what you said, Charlie, because it relates in a way to have a highly unusual interpretation of logic, which Saul Kripke made famous, which is this idea of possible worlds. But in situations where something seems to be unique, we do use some loose sense of plausibility when we're trying to assess it or even piece together a story. And a crime could be something that's a one-off bizarre event, right? But we piece together parts of it that are repeatable, like a footprint or something like that. So which is why it has repeatable aspects inside a non-repeatable combination. But the other way to think about it, which is fun, is to think that once you have a set of plausible forces and causes with which you make a mental model of the world, in some sense you have all these simulations. And when you say that something is pretty invariant in your state space of possible phenomena, you treat that as credible. And that's where the sort of Bayesian way of thinking about credences works. It sits in that kind of zone. So I like that framing.
I think you said it really well. Yeah.
The
relation to like logic and
how
we come to know about things that we don't directly observe.
Yeah, it's something I haven't looked into enough, but I plan to at some point, like Kripke specifically. So some time ago, I answered a Quora question about like what's the question you're really interested in, the one thing. And I was like, well, it's hard to say one thing, but then I thought, well, I like to sing the praises of the invariance perspective wherever I get a chance. So I said that the holy grail of computational neuroscience is understanding symmetry. And 2 weeks ago, we talked about keeping the map separate from the territory. And Karthik and Himanshu can testify to how much I've irritated them trying to discuss this issue of when is it the map and when is it the territory? Because with the mind, it's sort of both. The mind seeks, discovers, and creates invariance. So talking about this, there's all kinds of traps that one can fall into. But before we get to those, we can just list a few of these. Oh, okay. I was planning to put that one later, but so check out this is an example of a kind of motor invariance. Hopefully this works. You move the chicken around and its head stays incredibly still. Anyway.
There's actually, this made me, reminded me of, back to our old discussion of goal-directedness. I mean, there's just such a clean tie between variance and goal-directedness. In the sense that the goal is the invariant aspect of what you're trying to achieve. And and then it could be a very simple goal, such as picking up a glass. It could be a more complicated goal, but and what's interesting is that you can have a sophisticated goal that is, let's say it's, I want to be successful in 10 years or whatever that is. And that successfulness is the invariant there. You know, there's so many different situations that sort of fit that criteria, and that's sort of the symmetry there. I mean, I think that's a pretty exaggerated example of a goal.
No, I think it's a good example because it's like, it reflects a sort of paradox about humans, right? That we can posit an invariant and we can understand the sense in which it's invariant, but we can't necessarily understand the mechanisms of how it's maintained. That's part of what our job is as neuroscientists. So in things like color constancy, we impose invariance where there isn't actually, or in the world. And these top-down kind of examples are always nice. One of my favorite examples is octave invariance. And partly because it seems so natural to us that we forget that there is little or no evidence that animals have anything like this. Octave invariance is the idea that the notes, say 12 or however many that you divide up an octave into, like you can shift a whole tune up by a certain amount and it sounds like the same tune, or C and then C an octave higher, there's something similar about them. This there's all kinds of research about this, how it arises and whether it's a kind of purely mathematical phenomenon, and very difficult to test in animals. Earlier they thought all human beings had it, but recently there was a paper doing the rounds showing that there was one tribe in South America, I think.
Simani people in Bolivia. So
yes, in Bolivia.
This was the study that Josh McDermott and his group did in the Bolivian Andes, and they showed that these people don't have the octave invariance.
So
it's not really
regardless, it's an absolutely fascinating topic issue, because they have all kinds of cultural differences that where I think the men and women don't sing the same songs. So there's all kinds of stuff to get into there. I can send out this paper if people are curious. But the point is that there are plenty of invariances. Like if you're interested in framing things in terms of invariance, then there's no shortage of riches for any even minor phenomenon, from motor control all the way to higher cognition. And one of my favorite points is that analogies and metaphors are themselves symmetries. So classic GRE style, SAT style, A is to B as C is to D. You can formalize this, make it look really, really obtuse, where we say that the relationship between the ordered pair A and B is equivalent for swapping out the pair A, B, and C, D. So there's a set of pairs in some meaning space, some region where you can extract such pairs, and you can just keep swapping them out. Dog is to puppy as cat is to kitten, goat is to kid, and you can just keep swapping those out. And one of the things that I've long been interested in is how, in fact, I'm more interested in this than in consciousness. I want to know how the brain does this, how the brain creates metaphors and analogies. If we can solve this, then I think I don't care about consciousness.
But have you seen I was just introduced to this, and I sort of hadn't believed I hadn't thought of it earlier, but the Amos Tversky work, where they make these like parallelograms, where if A is to B as C is to D, then you also have A is to C as B is to D.
Like a more elaborate analogy?
No, just if you have A and B as a pair, and it's analogous to C and D. So like king is to queen as man is to woman, then king is to man as queen is to woman.
Right.
I'd never thought of it that way.
Yeah, I used to get a great kick out of this when studying for the GRE and stuff like that. There's two ways you can frame this. So one of the most refreshing places to read about metaphor and analogy is in this absolutely bonkers book, The Origin of Consciousness and the Breakdown of the Bicameral Mind. It is like, I highly recommend it, even though the neuroscience part is very dated and the overall thesis is bizarre. The idea is that some form of consciousness in humans did not exist prior to around 1500 BC. It's not what philosophers would call phenomenal consciousness. It doesn't mean that people weren't experiencing things, but he thinks that this notion of a narrative center of gravity, a self-narrating person that sort of talks to themselves, only existed after the Bronze Age collapse, basically, in the Near East. But what's cool about the book is that even though the overall thesis is quite weird, the specific things that he asks about are rarely encountered. For instance, what he really does well is ask the question, when did the human body become a metaphorical container for abstract attributes? And just the question is excellent, regardless of what the answer is. Like the idea that courage is in the chest or the stomach, or something is in the heart, soul is in the breath. Very often it was in the breath around the world. So his explanation has something to do with warfare in the case of Greece, ancient Greece. So it's more or less, he uses textual analysis to kind of infer changes in the self-conception of humans. But he has a fairly systematic way of talking about metaphor. Yeah, so I recommend this. It's very well written also. But he has this idiosyncratic terminology where you have the initial, so you have a metaphrand and a metaphor. The metaphrand is, let's say, the more familiar thing that you're going to be using. And the metaphor is the thing that I'm attaching to it. So food is the metaphor. Okay, so I think I said that wrong. So metaphor is the thing that is literally understood. So if you think of consuming ideas as a form of eating, and that's the metaphrand. And then what I like is that he introduces this concept of paraphiers, which are sort of other things that sort of come along for the ride once you establish an initial metaphorical link. So if you say that consuming ideas is like consuming food, then other analogies start to sort of suggest themselves. So for instance, you could ask, well, in that case, what's the brain? Or what the digestive system is like the brain, and maybe junk food is like in Mad Magazine. Mad Magazine is not that bad. So, but yeah. So the idea of an extended metaphor, which can sometimes become quite ridiculous, grows out of the initial seed. It's almost like each half of a metaphor has are like these waving limbs of an octopus that kind of wants to make connections. And I'm sure anybody who's had one of these free association conversations can relate to this, because it's like, oh, once one connection is made, things start to it's almost like crystallization. Things start to just pop out from a center. So, so all that was sort of a preamble to getting to information. And what I've been thinking about is that information is some sort of invariant. People disagree about what information is. So here I'm kind of black boxing it and saying that, well, whatever you think about it is now, there's something about it that's like an invariant. And I myself cannot articulate the various transformations with respect to something is invariant. But the thing that came to mind was this section of meta-magical themas. Have any of you read this? I probably haven't read the whole thing. It came out after Gödel Escher Bach. It's he basically replaced Martin Gardner he did a regular column, I forget, maybe it was Sam, of like puzzles and things like that. And Metamagical Themas is an anagram of Howard Gardner's column, which was, I think, I forget what it was. But I, for some reason, remember this diagram. I don't even remember what the content of the essay was, but this diagram I thought was a really nice way of expressing something that human beings do superbly well and barely even pause to contemplate, which is we have all these different, radically different typefaces. In this case, all different versions of the letter A. And if you think like a machine learning person who's trying to interpret the lower levels of their neural network, you might think, which features am I using? And you may find, once you think you have a feature that is definitively a feature of the letter A, that some other example of the letter A violates that feature. Like things like closure, things like whether it's an acute angle, things like whether there's a crossbar. All these things are violated by one or more of the examples. So whatever it is that we are representing has a fascinating type of invariant structure. And there's a lot you can think about just here. What the transformations are that we are able to ignore, in a sense. So keeping that in mind, we'll move to like the main kind of topic of information. Well, most people don't actually frame it in terms of invariance. So it's something that I think makes sense, but for some reason it doesn't come up. So when we step back and ask about information, best place to start is with the informal, loose connotations. And one reason is that despite the existence of formal approaches, there's immense confusion about what information is. And like you pick two papers or two textbooks and you find slightly different notions. And even in the physics community, I've seen a lot of disagreement about specifics of the thermodynamics of information. So to start from ordinary language. So long before information theory, there was the idea of information as a kind of outline, concept, an idea. And those are they're like suitcase words, right? They don't really mean anything. But I like the fact that the word shape is in there. And shape, not just as a thing, but as a verb. And that's like something to bookmark, because it's something that we will kind of want eventually for a cognitive way of thinking about information. This definition points to the word form, which has that kind of idea more clearly: contour, figure, shape, and outward appearance. But the verb, I like the notion of giving shape to something, which is often implied by the original usage. So I'm trying to shape something in your mind when I give you information. And this kind of puts this into context because it's been used for a very long time in theology and philosophy to mean an archetype or an essence of a thing. But now we have a new way of framing essence: invariance. And unlike essences, invariance sits in this nice midway zone between a completely abstract concept and something practical. Because, and the reason I like the word invariance is that the word variance is sitting in there. So to posit something as an invariance, it's sort of obligatory to think about what the transformations are. When you say something is an essence, you kind of have this notion of intrinsicness, and you're not asking whether there's a way of testing it, and speculation ensues. So with that, we can come to information theory, which I haven't really put too much of all this stuff in there, but it was a major revolution in thinking. And it starts by kind of dumping a lot of the connotation of information. And I like how he does it. Frequently, the messages have meaning. That is, they refer to or are correlated according to some system with certain physical or conceptual entities. These semantic aspects of communication are irrelevant to the engineering problem. But despite that, maybe because of that, people really paid a lot of attention, and not just engineers interested in communication. The significant aspect is that the actual message, not defined what a message is one selected from a set of possible messages. What's great about this is how clear it is. It's completely operationally defined, subjective to the user, as you want from an engineering tool. Most of you have seen this diagram, I assume. You have an information source. They are interested in sending a message to the receiver. So there's a transmitter. The signal can get corrupted by noise along the way in the channel. And the receiver basically decodes the message. A lot of this stuff kind of evolved because of cryptography in before and during World War II. Well, you don't often see that in the presentations of this stuff. Like Shannon's, this same work was originally classified. The interesting thing is to contrast this with how we set up a dynamical system. When we set up a dynamical system, we are not thinking of sending and receiving explicitly. We're thinking about forces, a state space, and we're interested in dynamics. So it's quite a different way of looking at something, and it's a different system. It has a purpose. Dynamic system need not be doing any specific job for us other than prediction. So a key idea with Shannon's approach to information is to count possibilities. Like you said, the message is one of many possible messages composed of many possible symbols. So there's a finite number of possible states of a system. Those could be, letters or bits. In addition, there is a set of transition probabilities. So from each symbol, there's a possibility that something else is the next symbol. Probability that if the system is in state Si, it will go to the next state Sj. And that's a Markov process. Some of you will have come across that in stats. So basically the idea is that the receiver is trying to continuously reduce uncertainty in what's coming in from the sender. The idea is that because of noise, they're not going to just wait and see what happens. They'll try and predict what's coming and maybe correct it based on if there's a flip or something. So they need to use knowledge to fix what this is. So that's why it's treated as a random variable. It's not exactly a random variable, but because of the noise, it's helpful to think of it as a random variable, the symbols that you're sending across the channel. So what Shannon does is come up with a way of quantifying this. And it's just how do we quantify, and then we can make some theorems about information engineering, communication engineering, with the help of this new tool. So can we define a quantity which will measure in some sense how much information is produced by such a process, this random Markov process, or better, at what rate information is produced? And there, he justifies the form, which you've probably seen before, this P log P form. Initially, he has a kind of informal way of talking about it, that we want when you add a new symbol, you want a particular kind of addition to take place in your information. So if you write down all these criteria for what you'd like from a well-behaved quantity that captures information, it should be continuous. It's a monotonically increasing function of n. So what that means is that if I have a bunch of symbols, all of which are equally possible, then that is a situation where the symbols are very unpredictable. And in that situation, any symbol you receive is maximally informative by virtue of the fact that they're so unpredictable. So what initially takes some time to get used to is the idea that from the Shannon entropy perspective, information is about information you don't have yet. It's like, another way to think about it is as missing information that will help you reduce your uncertainty. So if you receive something that you already know, it's not very informative. If it's completely determined by what you already knew before, it has zero information value. So there's three criteria: continuous, monotonic, and broken down. Actually, this next slide.
So it's something like if the statement the sun rises tomorrow, it probably contains no information, right? According to him, because there is no uncertainty in that, and it pretty much rises every day, right? So
very little uncertainty. It might, depending on the time scale you're looking at, there's some uncertainty.
Right.
Asteroids and such. But yeah, that's basically the idea. This other paper I found kind of explains those criteria in a slightly more readable way. This first one we already talked about, and so the inclusion of an impossible event should not change the value of H. That's nice, but it's always part of justifying the log formula. But what does the log formula actually look like? When you have two possibilities, so there's like two states with a probability P and 1 minus PQ. You can then look at how information varies with the probability. So for P is equal to 0.5, that's the maximum uncertainty, and that's where you get the most bits out of it. So the most unpredictable system is conveying the most bits. And bits, one point to keep in mind is that bit stands for binary digit, but in the context of information theory, it's not the same as like a bit in a register, like, or in a computer. It's good. There are two different concepts that have the same word associated with them. Bit in this context is a unit of measure of, and it's typically used for bits per symbol or bits per unit time for how you're transmitting something. So it's distinct from how many bytes you have on a hard disk. So yeah, basically information is capturing the idea, tell me something that I don't know. Stuff that I don't know is the information. So one thing that I was sort of hunting for the past few days was, well, what exactly is all this for? Like when somebody gives me a number, what do I do with it? It's very useful in engineering. And this theorem is quite cool. So if you have that noisy channel, he showed that as long as the information H in the that you're sending is less than or equal to the channel capacity, which again you can calculate using logarithms, then you can always transmit over the channel with an arbitrarily small error. And if that's not the case, there will be some error. And what's cool about this is that the theorem makes no reference to how noisy the channel is. So it's a very general statement that it doesn't construct, all the encoding that you might want, but it shows that there necessarily must exist one. So in a way, it kind of frees the engineers, or gives the engineers the confidence to hunt for these things once they know that they're in the right bound with the bit rate with which they're sending something. So there's a whole lot you can look into there, which is juggling logarithms and probabilities, and it's not too complicated. But for our purposes, it's what do we do with it? What do neuroscientists, cognitive scientists do with entropy? And this tutorial is pretty good. In fact, and I want to go over it carefully because there's a lot in there, and they've even got some MATLAB toolboxes that people could use. But so they have this big picture view, and like a lot of us, they were trying to address the question of someone like me who's like, what is all this? what do we need information theory for if we're not communication engineers? So information means different things to different people, but in neuroscience, information is frequently invoked when discussing information encoding, information processing, and information storage, memory. So all this time we've been talking about dynamical systems and gotten used to this completely different way of thinking. But this is almost like going back into the mainstream of neuroscience, where most people think in these terms. Even if this thinking does not actually constitute any kind of mathematical model, the framing is that the brain receives information from the outside world, transmits it among brain areas, among neurons, processes it somewhere or everywhere, and then transmits behavior back outside to the world. But even people who think that way will ask, well, what do I do with this quantity? And so this paper kind of explains some benefits of using the actual tools of information theory. So there's a type of model independence that exists in information theory. And what that means is, in the statistical sense, you're not really assuming that much. well, you're not really assuming any dynamics, which from our perspective is like, hey, dynamics is cool. But from the perspective of analyzing data, it's nice to be able to analyze data that's sort of agnostic to certain causal factors. But I say sort of because there's a big caveat there. It can be used with different types of data. This is an interesting point. So they're saying that regardless of whether you're talking about spikes or fMRI data or completely unrelated, like physical quantities, you can talk about their Shannon entropy and compare them. I guess I understand that. I'm a little bit, I'd like to see in more detail how one actually does that. But I think they have some citations for that. This is cool, and I was not completely aware of this. It's capable of detecting linear and nonlinear interactions. This is something to keep in mind. Is multivariate. I guess that's good. Which this relates to point 2 actually. It produces results in general units of bits, and this facilitates straightforward comparison between cells, brain regions, animals. You can compare everything if it's in common units. This ability to measure effect in bits allows for direct evaluations of effect sizes. I have no idea what that means, but it's something to look into because it sounds interesting.
That means you can get something published.
Okay, so what I said about, well, sort of, and I like that's great about this paper is how upfront it is about these things. To be clear, information theoretic analyses typically require some assumption. Frequently, it is assumed the system is not changing through observations. This is a big one. And again, coming from the dynamical perspective where the change is primarily what we're interested in, this is like the exact opposite end of the spectrum. A neuron that encodes the stimulus at the beginning of the experiment will do the same at the end. This is rarely the case, but I sympathize with anybody who has to make this assumption because you have to start somewhere when you're analyzing data. So it's you can't really knock this. You do have to do this.
I think it's only sufficient to assume that the system is not changing in its function.
Interesting. Yes. Okay. But the system versus the components, there's a...
Well, components are the system, any parts of it. That a specific system or a specific component that you're observing is, the next time you observe it, will still perform the same function. It may be the case that to use maybe the transfer function it was using may be slightly different and maybe like state dependent or whatever, but the role it's playing is the same. I think you don't have to assume that, everything is the same. You can relax on the part that the data that you're going to get may be slightly different based on,
Oh, you meaning that stationarity and things like that are not essential?
Yeah. Like a neuron might behave differently at night and in the day in terms of its actual values that you're computing,
right,
because of its environment. But it's doing the same thing. It's trying to do the same thing.
Yeah, that's true. And again, this is sort of a benefit that when you're just looking at how the variables interact, you don't have to assume how they're causally interacting. Underlying relationship with the variables understood need not follow a predefined model. So that can be quite useful. Again, I guess should be obvious by now, but information theory analyses are not capable of producing models that describe how the system works. So it's which is fine. So this is important. That, for instance, the information theory analysis does not tell us if the neurons are related via an excitatory or inhibitory interaction. So it will tell us that they're interacting in an interesting way, but not what type of interaction that is.
So I have a question here. So is the brain, I mean, when they talk about systems here, do they talk about part of the brain as a system, or what do they mean? Or my second question is, when they say system is not changing, do they mean linear, like time invariant or time variant, or what do they mean? I mean,
They can't, well, if you can talk to Karthik about what the actual spike trends look like, they're not very LTI, but you can do some processing to detrend it, and there's all kinds of stuff that you can do to pull out, to do things like extract Granger causality. Like Granger causality works with certain assumptions, which are not generally held by like a raw spike trend. But if you detrend it, there will be situations where you can say definitively that this particular bunch of spikes was caused by this one, and you're using one of the sliding window analyses. So there's all these different types of things you can. You may have to massage the data a little bit to satisfy the assumptions of the statistical method that you're using. But these may actually be more robust than many statistical methods. That's the impression I'm getting. As long as you can, because you can just use the data to and resample it to get your probability distribution in the first place. You don't have to necessarily posit a separate probability distribution in a model-dependent way, in the statistical model sense. So there are things you can do, which people often do nowadays when they're trying to get p-values in a non-parametric way. Right. So this I thought was cool. I'd like to maybe look into this a little bit more. So they showed that using mutual information, which is just an extension of that same log kind of formula, you can pull out things that are not visible from correlation alone. So they have one of these things, descendant of Anscombe's quartet sort of thing, where in the correlation shows nothing for the blue and the green plots, but the mutual information does actually extract something. This is cool. Definitely, if I were doing this type of experiment, I would try it out, I suppose. Karthik, have you tried this sort of thing?
Mutual information, no.
Yeah. To pull out a nonlinear interaction.
Johan, we've done a little bit of this with neuroimaging data with Joe Lizier here at University of Sydney, and for most of what we've been working on with blood oxygen dependent bold data, right? It's quite temporally smooth and spatially smooth, and so far we haven't really found too many differences between MI and like typical Pearson's correlation. But I think we're at the moment, our hypothesis is that's mainly based on the fact that the bold data is kind of so impoverished with respect to these kind of temporal relationships. We're starting to work on some ways of trying to fix that problem. But
because the lesson I'm sort of getting is that there's a hybrid modeling philosophy that we should be adopting, which is to take the best bits of each of these methods whenever we can and use one to constrain the other. And this Ram actually mentioned this in an email, this idea of complementarity, which I wasn't really thinking about, but it's a nice, I may be misusing it slightly compared to what Niels Bohr meant by it, but I was watching a talk by Robert Speckens on the invasion of physics by information theory. I watched it a little bit, but I liked this initial framing because it relates to this debate that I've been sort of conversation that's going on about, well, when is the system itself doing information processing and when is it a dynamical system? And it's really a sort of two worldviews. The dynamicist approach is that we're describing the system itself in what we sometimes think of as an objective way, because we're not actually putting ourselves in there. Our guesses are not necessarily baked in any obvious way. It is sort of there in a way, but it's not clear. Whereas when you talk about probability and you have a kind of distribution, your prior understanding of the system is very much front and center. So these two approaches are why the information theory looks weird from dynamical systems and vice versa. But the ideal thing is to kind of find a way to work with both. And like I said, for one to constrain the other if possible.
Can I jump in here with something, Johan, that's a curiosity for me? So I agree that a lot of neuroscience approaches, particularly in the kind of interpreting neuroimaging results, have kind of used information theory conveniently in the sense that they've said, oh, we've got this linear model of, receptivity, processing, output that's kind of, stayed around and since the 1950s of cognitive neuroscience. And we're starting to try to map all of our imaging results onto that idea of this kind of like linear processing machine. And through that lens, I think information theory can lead you to the wrong kinds of conclusions. It can make you think that there's a packet of information that's being sent somewhere and then unpacked, and then, oh, look, the message that I just got passed, and let's send off to another region. And I don't think that this is a particularly useful set of analogies for us to be using for understanding the brain. Dynamical systems is sort of in opposition to that, right? And it sort of says something like the action of the system is the computation. The trajectories of the system, the way the system coordinates, is it computing in some loose sense. So the part that's fascinating to me is that modern interpretations of information theory actually kind of got born out of one of the heroes of the dynamical systems approach, Randall Beer, right? And he's a dynamical systems, theorist through and through. He's got these beautiful models of little automata that can basically learn how to interact in the world through, genetic algorithms and trajectories of dynamical systems. And he said, well, maybe we should try to think about how these systems or descriptions of the system are changing over time. And if they're changing in particular ways, that's consistent with the idea that they've anticipated, or they've reduced their uncertainty about something, or they've stored some information, quote unquote, so that they can then use it at a later date, the next time they receive this similar input. And so in a weird way, it's like one of these Gordian knots, right? Where like the idea was born in engineering, and as it stands, or as it stood back then, is not really compatible with our models. But then people have come along and gone, well, what if we like take it and put it on here? And now you've got this weird Voltron-y thing, but it actually kind of makes sense to me. So I'm really curious to know both, what yourself, Johan, but what the group thinks about this idea of like taking, dynamical systems is almost sort of like the way that the system has to be organized under the hood. But information theory might be a really convenient way to describe the way that the dynamical system's acting in particular contexts. So I don't know, does that seem too Frankensteinian to people, or does it, it makes a lot of sense to me.
So in the neurophysiology or electrophys world, I would say the usage of information theory is probably even more like awful than because I don't know anything about how imaging works. So I'll restrict it to electrophysiology. Like when people usually do this mutual information, they are not really using it as an alternative for correlation to say that, okay, we have no understanding. So they don't start with the premise that, okay, there are these bunch of neurons, or the population response of a given area is something. Let's figure out what kind of a relationship they have. And let's see if that relationship is of any significance for us to explore further. It's just something that they churn through the cycle. They won't even do a correlation. They will just do this cycle and say like, oh, look at it. There is mutual information of 0.001 or whatever. And then that means there is something. It's not zero. That means there is some connection between them. They don't go in and analyze the scope of the connection between those two neurons or two areas when they talk about mutual information. They're not talking about its linearity versus non-linearity. They're not talking about like what might be the actual stimulus that can be encoded or attached or slapped onto that information value that they're suggesting. All they're saying is like, oh, we presented this broad input to the system. Let it flow through the network. We'll figure out whether neuron A in area 1 has conveyed some information in neuron B in area 2. So it's all like extremely ad hoc. And I think if you do want to do it, I think I believe there is a principal way to do it, but I have not seen it as yet in the field. But in general, I kind of agree with Mac, like it's possible to bridge these two. Like you don't want to be dismissing information theory outright, but you have to frame it in a manner where you're ready to show what the symbols are or what the priors are or something like that, and proceed with that.
I think it's worth also saying, even though I like dynamical systems a lot, that is also just a perspective with which to describe the brain, and we shouldn't get too hung up on it as the only way, because there may be phenomena where it becomes clunky to use dynamical systems. And when I say dynamical systems, I don't mean in the trivial sense that the brain is changing in time, right? I mean specifically differential equations, attractors, bifurcations, whatever, like the actual toolbox. There may be phenomena where there may be an emergent level at which something like information passing, symbol manipulation is the right way to think. And I think it's something that people should be open-minded about, that their data, they may even start by trying to think of it as a dynamical system, but the specific types of invariance that they uncover might be conducive to a sort of almost like a whiteboard, or, like a mental whiteboard. In some sense, we want that too. It's just that I think simply asserting it is the wrong thing. And like you said, Mac, too many people are just sort of issuing a kind of promissory note for information processing that doesn't actually look like anything.
I actually think this is one of the more frustrating, but also kind of important sort of, I don't know which category this falls in, but when you're thinking about scientific knowledge and how we're kind of applying tools to test the hypotheses we're interested in, it's very, very important to separate what has been done from what you could do. And a lot of tools are used really crappily. And I've, probably done the same thing in multiple experiments, inadvertently. Hopefully you don't want to do it knowledgeably. But I think it's so easy to make the wrong assumptions of these things, particularly when you're doing work that's trying to kind of break new ground in terms of new ways of thinking about complex problems. And so I think one of the things we try to do really hard in my lab is like read old literature, but have this kind of little bird on your shoulder saying, be careful not to take their conclusions too seriously, look at their approach, and then try to think about how you would interpret their results, given what you know about what their approach involved. I know it makes it much harder and slower, but it's important to remember that, not to throw out lots of, particularly powerful methods just because other people have been crappily.
Yeah, I think, in fact, as a version of scientific training, one of the reasons that I end up gravitating towards things that I actually don't quite get is because if someone is really, really enthusiastic about something that I don't get, then obviously there's a kind of mismatch of worldviews, and there must be something in that way of seeing that I'm not yet seeing. So it's something to acquire in the same way that acquiring a skill is. Because if someone can see something in that way of thinking about the world, and lots of people do, a lot of these SFI people, Santa Fe crowd, like all this. Right? I'm not saying that they're always coherent, but the fact that a lot of interesting things are being said using this framework means that we should at least be, reach a certain conversance with it. And also, the reason I put this there was just to think that, well, we are in a sense using information in our colloquial sense to make the dynamical system in the first place. So it's something loopy about these things, right? Because we are being informed.
Well, yeah, and you're also using it to basically simulate a dynamical system,
right?
Right. So
exactly. So, but I'm glad that Mac brought this up, because I was actually leading to this very critique, which doesn't necessarily attack information per se, because information theory is just a tool, but some of the paraphrase of the metaphor, which is the coding metaphor. When is it appropriate to say that something has been encoded? When is it appropriate to say something has been decoded? This little cartoon conveys something that I would say the majority of neuroscientists think in these terms. That there's something that is coming in, maybe there's a little processing, and then it gets transmitted. Even when I'm thinking about the brain in terms of multiple areas interacting, I often am thinking not necessarily in terms of packets, but something on that is a little bit on the anthropomorphic side. I typically don't think of coding and decoding, but it's an easy kind of jump to make. So what I like this paper, it's not perfect, because again, this was a great opportunity to use the concept of invariance, and he's a computational guy. I don't know why he didn't use it, but this paper by Romain Brett, it's a BBS paper. It has all the fighting at the end. It raises some good points. the neural code makes it seem as though the brain must also be making the kind of inference that the experimentalist is making. Like if I am saying such and such neuron is sharing such and such mutual information with neuron, and I don't make any subsequent claims, you can create the impression that what the brain is doing is similar to what I am doing as an experimentalist in pulling out mutual information. No one explicitly does that, I don't think, but it's an impression that kind of that floats around. And that kind of leads to this question, which might be just a polemical, but is this a dualistic way of thinking? So the coding metaphor has these two parts. There's the world, and there's the encoding of energy or whatever you like into packets of information inside the brain, which are then processed and then decoded in the form of action in the effector. So these two components, encoding and decoding, are indistinguishable in behavior. I think that's a good point, because we don't ever see only one of the two. So we have to ask, we're forcing this metaphor on it based on stuff that basically comes from cryptography. And how are we missing something when we force it on the brain? So,
Johan,
yes.
at the previous slide, encoding and decoding doesn't have to be on the same stream. There is stimulus from outside to inside is going through, but in the meanwhile, a thought is coming from inside to outside. That is considered motor action versus sensation. And they are not in the same units. They are not, it is not really encoding and decoding the same piece of data, same piece of information. They could be doing different things. That is how I look at the dual part of the brain, the perceptive part and the cognitive part. So
I think his point is that
I agree with the first statement, but the dual component, encoding, decoding are indistinguishable in behavior. I don't quite know what it means by that. I haven't read these papers. I don't know. I'm saying that
I think
one is sensation, the other one is action.
Well, basically, you cannot actually look at what an animal as a whole is doing without actually seeing behavior, because even sitting still is a type of behavior. So that's one way of thinking about that. And the other is that to really unpack the code metaphor, you're saying something like when I make a code, I'm taking something, reformulating it in a way that maybe is more condensed or something like that, like an MP3, right?
Yeah.
And then the decoding is that is again unfolded in some sense. It may be that there are some parts of the brain which are like that, but even modelers rarely, if ever, make use of such an idea. So like even just the feed forward, like neural networks, artificial neural networks, are more like dynamical systems in that whatever there's no decoding really. It's just sort of activation, right?
Right. That's what I was getting at. There's no decoding.
Yeah. So when
of the signal, right? Yeah.
Right. And so there's the communication on the one hand, and then there's decoding, which like you sometimes think like when someone talks to you, you need to interpret what they're saying, right? So which is why the next thing I go to is the concept of anthropomorphism.
Okay, go ahead. Yeah.
Which is that buried in the notion of the brain as a bunch of things that communicate is the idea that the brain is a bunch of people, basically. And
yes,
I think I actually recommend people do this. Like when they're thinking about the brain, try anthropomorphizing it just for the heck of it, to see if you do get something out of it, and if you're missing something, like that movie Inside Out, right? Talking about the different things in the brain. It's okay, but the thing I found totally irritating, and which I imagine must have baffled a child, is like, how can joy be sad ever? Like, and that kind of gets to the issue of anthropomorphizing, because people need to have like believable characters need to have the range from, and they can't be monotone. They can't just be doing one thing, right? But at the same time, you want to have this rigid division of labor, of joy and sorrow and whatever, right? So, I mean, understandable, it's a kid's movie, but the thing that is not explained is precisely what the entities in such a communication network do with the information. So this was in the essay, that one of the essays I sent out, which I wrote, is that everybody thinks they understand basic communication and networks and somebody sending something to someone, right? Because we are all in networks and we can all relate to them. So, but even when we talk about human communication, that we only understand part of it, the transmission part, the Shannon stuff, or internet infrastructure. All the stuff that goes on, which we have folded under the heading of interpretation or thinking or even just reacting, we don't have a whole lot of a story for that. So even when we do anthropomorphize, it's the same black box showing up at a smaller level, which is if something is treated as a completely dynamic, deterministic system, we tend to think of that as a machine. But the fact that so many parts of the brain are not completely deterministic, they seem to have whims, right? They do something sometimes and not other times. And so the more you depart from predictability, the more it seems like a person, right, who may be listening and will decide what to do with what they've heard. They don't necessarily respond the exact same response every time they hear a particular word. So what I'm trying to say is that there is a reason that we anthropomorphize, and there is actually a similarity in the non-determinism of responses. Problems come when we decide that we've already kind of understood where to draw the boundaries. Like, is it the case that the amygdala is a natural unit or the nucleus accumbens? It may not be. Maybe I mean the individual neuron, it's okay, but then it's really, really hard to tell a story about 80 billion people. It's not like economics is going to give us any useful tools, or sociology. So anthropomorphization, I think, is something that, in order to understand its limitations, people should engage in it. Not in papers or anything, but just when they're walking around or whatever, because it's a really interesting way to get some intuition. And you may even be able to generate hypotheses that way, which then, once they find their way into a sober kind of publication, won't look like anthropomorphization so much. Unless it's in the form of information sending and receiving, which is the one sort of free form of anthropomorphization everybody has access to.
Johan, I was just listening to a podcast yesterday, Brain Inspired. They were interviewing Mark Humphreys. He's like a dynamical systems neuroscientist that just wrote a book called The Spike. It's like the journey of a spike through the brain in 2.3 seconds or something. And he said he played that same game. He anthropomorphized a single neuron and imagined what it would be like to be that neuron in the context of like someone reaching out to get a cookie from a table in a meeting room. I just thought that was kind of interesting. It's kind of like, the Einstein imagining is a beam of light kind of thing. It was neat idea.
Yeah, it's like the more of these tools you collect, the better chance you have of not getting stuck in the blind spot of that particular method. So the trick is to use these tools without like saying that this is the tool with which to approach this. So, but what about higher cognition? There is a space where I think we do need to talk about these things as symbol manipulation, and these metaphors do live somewhere in the brain, but they're very hard to talk about. At some point, some neural phenomenon corresponds to the information processing. Like if I say that person over there is pondering what I said to him 5 minutes ago, that's not exactly a metaphor, right? Meaning that there's some neural correlate of that pondering, which is not necessarily best described as attractors or even a chaotic attractor. Maybe it is a chaotic attractor, who knows? Do we have to, is this anthropomorphic? We already kind of talked about that. And In the case of some of the canonical examples of higher cognition, my favorite examples are just, adding numbers in your head, or, doing square roots, or things like that. How would you describe it without reference to information being in the brain? So it's like when you pull out something like, oh, I forgot the formula for such and such. Give me a sec. Now I remember it. Now let me apply the formula. Whether or not you're using pen and paper, the thing you're doing, if not sending and receiving within yourself, at the very least, something has arrived in your working space that you can symbolize and then manipulate using rules. And that becomes, introspectively, it's very transparent that that's what one was doing. So how do we get there from whichever perspective? We don't have to, because there's plenty of other neuroscience questions to ask before that. And all of this circles around the difficult question of what are symbols, which we have managed to not use that term. Did I use it at all so far? But anyway, what are symbols? And do we have a way of talking about neural processes as symbolic processes? Thoughts?
Could you expand on that some more? It's like what you're thinking about.
So like if I were to, like the most difficult or most complicated neural models that are dynamical systems will typically end with object recognition of some sort. So you end up with something somewhat symbol-like and with a reasonable amount of invariance that you might want. So my square detector, wherever it sits or however it's instantiated neurally, is invariant to size, position, color, all kinds of things. And if I need to do something involving squares, that relatively compact representation can be fed into the motor system. So it's like press the square thing with your elbow, even though I've never done such a thing before, is easy, right? So I have not hard coded that signal, that symbol of whatever it is that represents the square to my elbow, or to the command that represents press something with your elbow. So there's a many-to-many kind of mapping from things that I am capable of recognizing and creating symbols for. I'm using the word symbol here loosely because some people might think of categories as different from symbols. And so, and I don't have strong intuition about this because clearly animals are capable of categorizing things, but they don't seem to do anything that we would feel obliged to call symbol manipulation. But if people disagree with that, I would love to hear examples of where you think the phenomenology of the animal is symbol manipulation.
If an animal uses a tool, then is it a symbol or is it just a categorized thing?
I don't know. What do you think?
I mean, I am agnostic, but I wouldn't mind you calling that a symbol.
What, the tool itself?
The capacity for the animal to wield the tool to get the task done.
Okay.
Would not simply stem from mere categorization. It has to cross that threshold, no?
So beyond categorization, what are you thinking of?
Like the same example that you gave with the elbow drawing the square or whatever.
Okay. Yeah.
Like if the animal is able to achieve the same task without using its body, but is able to manipulate something in the world to do that. The fact that it can make a tool or even make use of a tool, like some fish and some monkeys are like capable of like taking a stone, making a proper mortar and pestle, and then like the capuchins, they can sit and actually like break the nut and eat it. So yeah. Is that at that level? Is that level of tool manipulation something that the animal is kind of doing in some reflexive way, or is it symbol building?
Yeah, I like this. It's difficult to think. I find it very difficult to think about it because like how do humans do it, right? Like there are certain things that we don't need to overtrain, but you can like use a screwdriver to open a can of paint. You may never have done this before in your life, right? but when you happen to see the screwdriver, you'll be like, ah, that will work. There's a sense in which the whatever your representation is of the screwdriver, in addition to it, the category as an isolated thing, which is like a flag saying ding 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 ding, there is a screwdriver in the vicinity or in your hand. There's something else, right? Which is all the affordances of the screwdriver, what it is capable of doing, are sort of also in there. And what we're kind of saying is that associative network without repetitive training can come into relation with a goal, with a stimulus which is related to a goal. Very hard to frame it. Like I can say it, I don't know what it looks like as a model.
But that doesn't really seem symbolic to me. The way I see it, it's more just simulation.
Simulation on the part of?
On the part of the monkey, like simulating in their head the outcome of certain actions.
I have a question about symbols. What's the relationship between symbols and bits of information?
There's two answers. The symbols that are processed by information theory are what give you the probabilities. So if you're interested in a discrete set of things that you're communicating, then you kind of already have to decide on them. But the other way of thinking about it is less clear. Like what is symbol? Like this is the open question. Which I kind of ending with this, which is when we work with symbols, it's almost like we're working with like the flag placed on top of a mountain, on a mountain peak or something, right? It's like the visible, like if I write down x squared plus 1, I tend to think of x as a symbol, right? And when I'm manipulating, the visible part of my manipulation, x squared plus 1 and something, is moving around these discrete things. The natural tendency is to assume that that's also what's happening. Like there's a corresponding phenomenon happening, but maybe that's the least interesting part of it, because that's in some sense the consequence of rule-like structures that we associate with those representations. So I know what.
Oh, sorry.
Eli was going to say something. Yeah.
Sorry. Yeah, we're both using the same iPad. One idea of symbolic representation that I always think of in animals, which we use for behavioral tasks, is the symbol holding of same and different. So like it's a very simple paradigm where you hold up, you go circle to circle versus circle to square. So same is circle, circle, different is circle, square. And then you ask the animal, okay, here is two pieces of food where there's clearly difference versus clearly the same. And if you train them on the same, then by more than chance they'll go to the same. So which I guess in that case to me is a direct evidence of like a symbolic representation in their mind of the concept of same, and then they've mapped it to a symbol, and then they actually then behaviorally respond to it in a real life environment.
That's cool. So I typically have never thought of a relation as a symbol, but I don't have any strong intuition about it. So I like that actually, because it's like the way that symbols enter into relations with each other is what makes them symbols in a sense.
Yeah, like we teach them the relationship via the symbols, right? So they're holding on to the symbol, but they understand the relationship as well, perhaps. I don't know.
But this, I think this is actually really crucial, right? Because what people want to do there is they want to go beyond that and say that there's now a symbol in your brain, rather than the fact that you as a dynamical system have coupled with particular differences in the environment in certain contexts and learn how to interact with that thing that is a symbol in its own right, like circles and squares, whatever they're symbols. No one's going to deny that. Whether or not our brain needs to hang on to the idea of symbols and use those as currency for determining how it will respond in an upcoming trial is I think there's the rub right there, right? And to me, I don't think that's a sensible way to ask the question. To me, there's a system that has set of capacities. One of them is to join certain input-output relationships. And in doing so, in the particular context, you get trained that this kind of input-output relationship is the reward one and the other one isn't. And so the next time you come along with something like it, your brain gives a little bit of a match to that next input. Now, it doesn't have to be exactly the same. It could be analogous, and that gets quite fascinating when you start to jump in with your sort of new interpretation of this kind of context you've never seen before. But that does not imply that you need to carry a symbol in your mind or a symbol in your brain somewhere where that you should find the distinction. And I think that's where we get a lot of muddled thinking in neuroscience, is that people think that, or at least they use the words that suggest that they think that symbols are somehow inherent within the brain or inherent within the mind's function.
So I kind of agree with Mac here. We can think of symbols as a sort of cognitive activity rather than something that is an imprint of some sort. So here is another question I have, because this is something that Johan and I, we have all been talking about for some time. So it's not like we have answers here. So this is an example that Himanshu probably likes the most because it's about salt. There are these monkeys that were abandoned in Japan in the sea, near the seacoast. And when they were given potatoes for the first few generations, they were just eating the potato as such, the sweet potato. And then they realized that, accidentally they dunked it in the seawater. The seawater seasoned the sweet potato, and the animals started making that a practice. Is that some sort of the fact that the animal has now realized that it can season its food and it tastes better and it keeps doing it? Where would you fit that kind of cognitive activity? Is that doing some sort of symbolic processing, or is it just conditioned reflex? I don't know how to answer this part. I'm open, but there are videos of these monkeys actually, like, once you give them sweet potato, they'll immediately rush to the coast, dunk it in the sea water, and then like eat it. It's pretty remarkable. And it only caught on in the last 1 or 2 generations.
Yeah, and to add to that same part of question is would you think of rewards as symbols?
I mean, I think rewards rely on an internal representation, and I feel like I'm not convinced that the existence of internal representations is distinct from the existence of symbols. Like, you have to have somewhere in your brain, like if you're a mammal, there has to be some amount of dopamine that's going to indicate some amount of value to you. And that is a representation, and that it is a quantity that's not a literal thing. It's a quantity that's a reference to something that exists in the world. I do want to talk about that. I also want to drop a super low-hanging fruit example, which is that animals are, a lot of social animals, especially primates, are perfectly capable of like assigning meaning to sounds. Like there are animals that have like specific calls that refer to predators, or specific calls that refer to like bees, or something. So I mean, I think that's pretty much like very, like, I think it would be very hard to deny that that those are symbols, because they're literally, like, if that's not symbols, what is? Because that's exactly the same way humans use speech.
Well,
So
Terry Deacon would argue that those aren't symbols. He would argue that they are, I forget exactly what his argument was, but there's a different, okay, here's what he would argue. He would argue that they are symbols actually, but there's a difference between symbols that we agree on by convention versus sort of innate symbols, and they're kind of very different things. But like humans differ by the ability to assign arbitrary meanings to or a meaning to an arbitrary symbol or sound or whatever, whereas animals sort of come with this reflexive, like they don't necessarily learn this arbitrary association to the meaning that there's a predator. It's sort of all reflexively built in. I just wanted to put that.
I mean, do we know that it's instinctual? Do we know that it's not something that's socially learned and agreed upon?
Yeah, I think one argument for that is just that animals, or like from the same species that live in very different locations and haven't been in communication for a very long amount of time, maintain the same calls.
I would say that we don't know. The verdict is still out on that, just calling all of it reflexive. I don't agree with Terry here. You can have the same animal like in different contexts behaving differently. We have not proven that yet. We are just assuming the same. I find that kind of attribution to reflexive behavior a Descartesian continuation of how we look at animals. This I mean, we can maybe even like come up with experiments with feral dogs versus dogs trained at home and see how they react to certain things. And I'm pretty sure they're not going to be the same. So I'm not convinced by that idea that all they can do when they see a predator is going to be completely reflexive.
I think what we can say is that so far, human beings have not caught an animal naming something in the wild or in captivity. It may happen, but I suspect that even with a small child, you can say this thingy here, and you attach a gibberish name to it. It's hard with dogs, for instance, when you would assign a word to some object like this ball. You have to do this over and over and over again with rewards in order for the dog to get it. They might have easier ways of doing it when it's a pack of wolves, but I don't think anybody's observed it.
I wonder how much that comes down to.
With Coco's kitten learned plenty of those kind of names, but I guess the gorilla didn't create the name, right?
Yeah, that's my point. The animals
but don't like, for example, dogs have specific sounds that they produce like when they're hungry or something like that to indicate to you that they're hungry, or
cats
isn't that yeah.
But that might be due to like vocal tracts.
I have a question with respect to we have three sort of sets of vocabularies. Well, we've got the information vocabulary, the dynamical system vocabulary, and now we're trying to use this word symbol. And how would we use it with respect to the vocabulary from each toolbox? Like, does a particular sound that indicates a predator or a word reflect a trajectory or a change in dynamical system state? And what is information with respect to the states or trajectories? How do these three fit together, basically? How can you use the terminology of one to define the other?
I believe it's like an attractor. Like that's how you would store information in a dynamical system.
But
yeah, I mean, you can assign symbols to different region of base space too.
You can quantize the space, assign symbols.
Yeah.
There's a field called Symbolic Dynamics, which only in the past few weeks have I started reading about it. And it's really cool in the context of chaotic systems, because you can get like a lot of interesting sequences. So like think of the Lorentz attractor, right? It's going along one side and then the other. If you just assign 0 to 1 and 1 to the other, then you can produce all kinds of really complicated binary strings just from this huge binarization of the state space. And people have argued that you can do computation with this, and for that reason, the distinction between dynamical approaches and a computational approach is meaningless. I think that's extreme, because the way of thinking is different when you set up an algorithm versus set up a dynamical system. So I think technically it's true that if you discretize, but the real question is not whether I discretize it, is some readout of the nervous system discretizing? I think the answer is definitely yes, right? But we have to ask how. So, and this is why the concept of symbol, I didn't build up to it, because I think everybody has intuitions about it that are probably not that overlapping. Because when someone says such and such thing symbolizes something else, there is a relation other than categorization.
Yes.
So the examples of animals using calls is a symbol in that sense, right? Because like whether or not it's reflexive or somehow learned or some kind of mutual reinforcement kind of situation. Like in fact, that's what when Himanshu just talked about the dog, right? It may be that there is a multi-person version of babbling. So when people talk about modeling speech is one idea that babbling is a way to create an inverse kinematic map. And what that is that the baby's babbling. What's happening is that a mapping is being created between what the baby hears and the muscles that produces the babbling. And the mapping goes from the hearing to the muscles. So it's from consequences to causes. And there are nice models of this, and it's basically the state of the art in speech production with Frank Gunther is this type of model. And what's cool is this is not error-based learning, and it's not reinforcement-based learning. It's a different type of learning. And it's basically learning what you are capable of. And the most important thing there is that your goal needs to be represented in perception space. So I need to think about what it is I want to achieve. It's like deciding to speak based on knowing what I expect to hear. And then that will filter back using the mappings that you learned while babbling. Now, when Himanshu said the thing about the dog, I was thinking about like a two-person version of quasi like babbling plus reinforcement, in the sense that animals capable of communicating goals will produce whatever kinds of behavior they can in it. And the dog will realize that some cries will irritate the human enough that they'll be like, what do you want? Anybody who's lived with a dog knows how that works.
Johan,
what? And the dog will sometimes then walk to the place where the food bowl is, right? And in the early days, if it's not a very attention-paying owner, the dog might try a whole bunch of different things. So it may not always be the same sound. Like even if it's the exact same breed, or like twins that are with different owners, you may expect that the sounds they make will be different because it's a feedback loop. And you would expect that, or at least that as a hypothesis, you can say that distinct tribes of chimpanzees may use a different set of sounds. If they use the exact same sounds, I would then be on the side of the instinct thing. But
Johan, I have an example from my lab. Okay, so I used to work with collecting, like doing auditory processing or sound processing of marmoset audio. So one of the most frequent calls that these New World monkeys, the marmosets, make is called a fee. It's supposed, we still don't know what they make, about 7 to 15 different types of calls. We still don't know what all of them are. We have some idea about 2 or 3 of them. So one of them is called the fee call, PHEE. It's usually believed to be something like an acknowledgement signal telling someone in the group, like, hey, I'm here, you know. That's kind of like, it's like, oh, I've not talked to you in a long time. I can't see your back, you know. Hey, so that's the kind of call that they make. So it's sort of like acknowledging. What you observe something very, very interesting in the nature of the fee call, which maybe for our ears we can't like really see. But then once you do a spectrogram of it, it's very different when an animal which is part of its social group is around the local environment in which the animal is. Maybe it can't see it. So there is a certain way in which the fee call is present. The frequency ranges are very different during that time from when the animal is fully isolated. And it's like, you know, crying for help or saying like, hey, I'm here, you know, check it out. They are completely different. You can actually like run any sort of a categorical, you know, decoder or whatever. You'll see that it's very, very different. So it's like, it's not just making a call. It knows, like, it's like also saying like, I'm here, buddy. I think it's like that attachment is also there, which is not there when the animal is in isolation. And it also is not there when the animal is fed back through an audio sample of a random marmoset making a fee call back. That is not there. So the animal somehow recognizes that this fee call was not made by a member that it knows. So it only replies back in like, you know, hi kind of stuff, but it doesn't really do it with that specific frequency that you would observe on the other when it is in its social group.
Yeah, there's no feedback, right?
Yeah.
That's interesting. So
that reminds me of in some Asian cultures, right? The intonation on the sounds is actually helps you determine whether or not it's a question or a statement, right? And so like to my ears, you know, growing up in an English speaking household, to me, they all sound very similar. But then to someone from that native culture, they can totally parse like 4 or 5 different ways of you know, understanding what sounds to me like the same sound. So it's partly due to like the umwelt, right? Like the part that we know how to pay attention to, the difference that makes a difference, or at least to us, the difference which we're ignorant. I think that's really cool.
Oh, I didn't actually bring that up in these, but difference that makes a difference was in the back of my mind when that's a famous sentence that Gregory Bateson wrote in an essay. I think he was an early cybernetics researcher, and he wrote this in 1970. And what's interesting about this idea, difference that makes a difference, is that it's in a way a contrast from the invariance approach, because it's sort of talking about information as that which the animal acts on. And it's like, well, like they're sort of like, well, all these things that are happening I don't care about, but this I do care about. So in that sense, it's a difference that makes a difference. But there's always the invariant part of it, which is that you have to kind of categorize a bunch of different families of experience in order to, because there are low dimensional things that all organisms have to do, right? Approach, avoid. So even at that level, there's categorization going on, and which is why categorization needs to be kept separate from symbols. This naming thing. Let's say that animals do have it. We can then build from there. And the reason I think that eventually symbols will be a useful theoretical concept in human just mental activity is just because the transparency of the introspection for certain activities is that you're working with all these things which have aboutness relations. This is about that, this is about that, this is about something else. And the aboutness relations are in addition to all the connotative links that are sort of like an iceberg, in the sense that it's not clear how deep they go. So a really, really high level set of examples involve humor. Like when someone is making a joke that operates on multiple levels, right? They are simultaneously referring to something in the literal way and using the connotations of both, and then working with a pun that operates on maybe something that hasn't been stated yet, involving the associative network of one or the other. So the fact that these things have a center that is present to our introspection, whereas the network isn't, like all the stuff that we're able to use in a kind of affordance sense does not show up except when you're daydreaming, and then you're not necessarily paying attention. But when you're using it, you're on the fly making use of the associations, but what you are typically aware of is some sort of center that you can move around.
So do you think that humor requires the objective kind of definition of symbols, or do you think that it's possible also to imagine a mechanism that is maybe associational, or, you know, as you know, part of the trouble here, right, that I think you're kind of, that's between a lot of the cracks of this, is that it's very hard to talk about cognition and cognitive function in the things that we're trying to explain, because they're so removed from the here and now, right? Like I could sit and think now about some basketball game I saw ages ago and had some move that I wanted to practice or something like that. It's got nothing to do with anything in front of my face, anything that I'm actually interacting with in the world, but I can do some work on that thing that's abstracted in space and time, and maybe even talent level, let's say. And so there's something about it that makes it's so much easier to talk about when we talk about symbols, but yet the way that we actually interact with it doesn't, to me, have to be symbolic. It can be still based on association and based on, you know, procedural memories and episodic memories and all these different things that are the capacities of our system. It's really easy to talk about them in symbols, but it's not necessarily the way that they work.
Yes,
I don't know if I explained that very well, but I think humor works in a similar way.
Could you elaborate on what you mean by the processing side of symbols? So when I say symbol manipulation, what does that conjure up for you?
Oh, sure. So I think that a lot of neuroscientists, when they think about symbols, they think about items, categories. You know, there's a thing, there's my grandmother's face, right? From the classic grandmother neuron thing. But that's the declarative memories. The memory of a thing, of a noun, is only kind of one way that brains can carry information from the past and forward into the future and to affect adaptive behavior. Another way is procedural memory, the way you can interact with whatever it is in front of you. So if you said, Mac, you've learned how to draw with a pen, and all of a sudden here's a piece of chalk, I can take the things that I've learned in the past from interacting with a pen-shaped object and manipulate them slightly so that I can now interact with the chalk, or a rock, or a piece of, you know, coal, or etc. Right? There's many different things, like a stylus. So it's almost like invariant to the particular thing that I've learned about. It's a way of interacting with it. And I think that learning how declarative memories, I shouldn't call them episodic, because that assumes that you've actually seen the thing before, whereas declarative and semantic memory can be an extrapolation from categories. Like I've seen 150 dogs. Now I know I kind of have like somewhere in my brain, there's a kind of section that has learned the dogginess of the thing rather than actually ever seeing an abstract dog, quote unquote. So declarative memories are sort of ones that you could sort of almost put into the noun category, and then procedural memories are sort of more in the verb category. And the interaction between those, to me, is what's really critical for us to understand, to understand how our brains are functioning on these really abstract levels. And as I said, I don't know if that helps to unpack what I was saying or not, but so to me, symbols are something that emerges from the interaction of those two.
Right, I agree, but I think that like there's always a few operations where whichever future dynamic explanation we end up with, I suspect that they will have concepts that are analogous to what we call symbols. And from the math examples are always the ones that come to mind. If I'm, you know, multiplying two-digit numbers in my head, how do I do it? I mean, there's various people. Some people can just do it without actually doing any symbol manipulation, but most people will like have a piece of paper in their mind, right? So the thing that they are consciously working with are symbols. Or someone with some mechanical intuition might think I need to have this cog and gear arranged in this way. Or you might
should we add in one caveat there, Johan, which is the way that it shows up to someone is that they're working with the symbols, right? It could be that there's a huge amount of non-conscious processing that's going on that is doing the real work, and it feels like you're doing some symbolic reasoning. You've got this symbol in your mind and you're comparing it to the same symbol and you're combining them together. But really that's an epiphenomenon related to some machination that's occurring under the surface. And to me, those are both hypotheses that we can try to test. I think this is one of the challenges with introspection, right? Is that like our world feels like it is omnipresent, yet it's completely impoverished. And like, you know, so much of what's happening in our day-to-day kind of lived experience is actually just the tiniest sliver of the neural activity that's ongoing that allows us to do things. And language is just a beautiful example, right? We think in terms of concepts that we want to explain to people, but we take for granted all this like ridiculous learning we've done of phonemes and sentence structures and the pauses in time when a sentence finishes, or the intonation that changes to the question versus a statement, right? There's all this stuff that we just completely ignore, yet our brain is taking in and soaking in all of that information and doing something with it that we couldn't ever do any of the work that we think is the conscious part, which is all of it, on top of it. So I think there's in some way I think we think about cognition a little bit too much through a kind of experiential lens, which is only one part of the neural activity.
So Mac, are you like, can we relate this to the whole like pre-attentive processing theory that we have like been accustomed to in vision and attention? Whatever you're suggesting, in the sense that what finally comes to attention are the symbols that we are manipulating, and then before that there is a lot of buried activity, which, you know, the psychologists would call as pre-attentive processing. Would you say that that is similar in characterization to what you're suggesting with language, or, you know, this?
Yeah, I'm not like intimately familiar with that literature, Kartik, but my guess would be that what we call the symbol that we think we're manipulating has just as much pre-attentive stuff going on with it as kind of necessary scaffolding as the pre-attentive stuff has. It's just that it's missing, the pre-attentive is just missing the sort of crucial neural signature that then pops it up into our conscious experience. Now, what that is a fascinating open question at which there's really cool kind of research going on at the moment across multiple different fields. You know, what is it that causes, you know, coordinated activity in your nervous system to differentiate between the, you know, the thing that you were attending to that you were conscious of and the thing you were attending to that you missed, let's say in change detection paradigms or in mask paradigms. And that is a really fascinating problem that gets really philosophically gnarly when you start to think about the subtle differences that are occurring in your brain that differentiate the things that you're aware of versus you aren't. But the key characteristic in a lot of these is that there's not just like some magical neuron that gets active or something like that when you're aware of something or not. It's really subtle distinctions. And one idea might be that in the language of dynamical systems, sorry, my dogs are just freaking out. Hey, one
information, Mike.
He did, right? He received some information that there's people in our front yard that have been here the whole day. One, to map this into the language of dynamical systems, one thing that could happen is that, and this is just hypothesis you could test, is that there's some form of bifurcation in the system dynamics that differentiates these two, right? In each case, the pre-attentive, let's call that unconscious versus post-attentive conscious, whatever boundaries you want to say, maybe there's some kind of a bifurcation such that the system is acting in one way in one context and now has a different type of interaction in another context. And the question then becomes, well, how would we differentiate those? Is it something like crossing a hop bifurcation and you all of a sudden get, you know, a coordinated oscillations between regions, as, you know, you might get out of the Pascal freeze communication through coherence story? Is it something like Sandahana's and Jean-Pierre Janjot's idea of global neuronal workspace, where you somehow have an ignition event which now differentiates the information and now it can be propagated? I don't quite even know what they mean by propagate and broadcast, but I'm just trying to draw sort of broad brushes here, that you can imagine there's going to be very, very similar neural activity in both cases, but a subtle difference in the dynamical properties, and that somehow comes with the signature of our ability to reflect upon it and experience it. But that's a fascinating open question. To get back to what you were asking, Kartik, I think that the signatures will be very similar, but just with subtle differences but for whatever reason, those subtle differences carry with them phenomenal character that we experience, we can, you know, interact with and carry forward, and we take for the whole thing, even though it's only a part of it. But I don't know if I feel like I've just waxed on a little bit. Hopefully that was helpful.
It's good that you said epiphenomenon, because I don't think we can actually use that term in this context because if people reliably have a particular introspective experience, the claim is not that that is an accurate representation of the neural mechanisms, but that it is an experience. So that there is something in the neural phenomenon that is conducive to me thinking that when I close my eyes, I see x to the power of 2 as two discrete things floating in the void. So something in my neural apparatus allows me to experience that. And it is without a doubt the tip of some iceberg of unknown size.
So something odd about my phenomenal experience might be helpful here. So I have something called aphantasia, which means that I don't have a vivid internal experience of my mental imagery. And yet I can do all the things that you're saying. I could imagine multiplying n by m and getting, you know, squaring that product, right? But it doesn't show up to me in any way. So to me, I view the experiential quality of that as an epiphenomenon because I can do all of it without experiencing it. But that's not to say that I'm wrong. Maybe it's happening, but I don't have access to it in a way that gets a little bit more gnarly. But yeah.
So it's a little bit like saying that clearly when I'm doing pen and paper mathematics, my hand and my brain and lots of things are involved, right? But there is still some logical structure that you can actually infer from the symbols themselves. Mm-hmm. And a lot of what mathematicians are doing now is related to this. And in fact, automated proof theorems and stuff like that are trying to really make the manipulations mechanical. It's not the case that human beings necessarily, or that all mathematicians are capable of the kinds of mechanical symbol manipulation that those algorithms do. But there are small examples of that. kind of thing, or at least the shadow of that phenomenon in the conscious theater looks a bit like that. So when I want to and you can just jump straight to the concept of language, right? So the thing that maybe I said this before, but one thing I'm very interested in is the structure of whatever it is that is prior to me picking a specific sentence to say. So if I, which is another way of thinking about what facts are. So if it's the case that I'm looking at my table and I say, let me say something true about the table. There is a green pen on the book. There are many, infinitely many true things I could say about things and their relationships with each other. In fact, all the true things that I say, other than there is a pen, will involve relations. Even there is a pen is a relation between the pen and my phenomenal field. So you can ask, what is the nature of that structure that contains many invariants? Specifically, they're invariant to all the different ways I could say it. I can say it in active voice, passive voice. If I knew many languages, I could say them in various languages. I could say them with like a jokey intonation or not. So I could, say a particular sentence to the tune of a song, So we can even blend invariances. I can make sure that I'm saying the thing that I want to say to you, but also say it in a sing-song way. So when you sort of cycle through all the different invariances that are guaranteed to be present just from the behavior, like what I'm doing is black boxing the behavior, right? I'm saying that I have no idea what's happening in the brain. All I'm looking at is the transformations that I'm capable of, or that somebody else could even use me as a black box, right? Here, transform this sentence into something about Star Wars, and that can work, right? So whatever it is that's doing all that, it seems to me a good chunk of it is about these relations between categories, and the categories then have further relations with each other, and those relations constrain what can meaningfully be said, like factually, and can also constrain how I can finish the sentence. Like once I've started saying something, if I want to complete it grammatically and not just end it, there's this, and that does have a dynamic quality, but what's recruited are not individual muscle movements. They're not objects exactly, right? There's something else. And what is that thing that has this quality? Like for instance, what is a pronoun exactly? When we refer to something, I say this is its name, and then later on, I say I'm using pronoun. So I'm not repeating the name. I'm using something else, which ties me back to this earlier thing. These are, for lack of a better term, some part of it you tend to describe using symbols, in the sense that so much of the specificity of the phenomenon is missing that what it looks like is what Peirce called, Charlie, what are the three things that he said? Schema, the three levels of C.S. Peirce's semiotics. So you have
there's icons, indices, and symbols.
Icons, indices, and symbols. So you can get a sense in which all of these things are used in the generation of language. So like I said, each of them is like a little conscious flag on top of an island that actually goes deep underwater. Like the roots of it are there, but the fact that those are the particular things that we are able to manipulate, and for which, like, I think global workspace is a good way to think about this. So I haven't actually read any papers in detail about this, but the way I understand it is that they're trying to say, to come up with theory of which things are conscious. And there's a sort of operational way. And even if we leave aside the phenomenal aspect of it, you can say that me being conscious of the set of things I am conscious of is a kind of potential for the simplified, like for all the categorized versions of that particular thing to come into contact with every single possible action. Like in principle, I could take my lamp to the stove, like do all these things that don't make any sense, right? Like, so what it means is that all those things have attained a level of equality. And that equality is the equality of is related to the quality of them all being part of the same sentence. Like one of those wonderful things about surreal humor is the number of unrelated things you can pack into one sentence. The potential to do that in a way that's really unconstrained by context suggests that in a context invariant way, some sort of representative, for lack of a better term, of that concept is like sitting in this assembly of candidates for incorporation. And obviously in normal situations, when you're working, when you're busy, when you're on a train, the set of concepts that you could just blurt out are more constrained. But if you had a couple of drinks and when you're with friends and who like to free associate, that number can be quite different. So it's just saying that this unit, which can enter into, freely enter into relations with all these other units, seems to have its own existence irrespective of whether you're even perceiving it. Like you can sometimes say a word without even having the perceptual experience of it until after you said it. So those are the kinds of things that for me are inching towards the symbol territory, which is not to say, but I think you're right in that the explanation of the phenomenon will involve flows. And so it's like as if the concepts are these huge things and there's little LED lights on each of them and they're moving around in the dark and all we see are those LED lights. But that's still a phenomenon that is of interest, you know?
Yeah, I think I found myself agreeing with a lot of what you were saying, but one thing that kind of occurred to me as you were speaking was that a lot of the features that we assign the symbolism to, I think are closer to features of language than they are of brains. It's almost like this thing that lives alone is this complex semantic language that we've sort of managed to build up and propagate over time and has been a force multiplier for brain development. But the neural mechanisms that support using that don't need to have the same features of the language. They use them, and they're almost like little things chasing each other around in a way that sort of improve one another's function and make them, you know, they help to differentiate them and things. But I'm slightly cynical that the brain will use the same structure that the language system has built. I think we're used to interacting with them, but our brains were around an awful long time before language came along, particularly as a language as sophisticated as the kind of modern languages we use to interact with one another. So I just wanted to put that flag in there. I'm okay with the idea of symbols. You know, you had this nice thing on Twitter last week where you said something like, you know, we need a word, probably one in German, that says something like a term that's really useful for theoreticians, but we can later discard. I think of symbols as maybe something along those lines, like representation, and just trying to come at it from a, you know, I'm empathizing with the brain here and thinking, why would the brain do it like that when it's been, you know, carved over evolutionary time in this other way? And there's a disconnect there that feels a little bit disingenuous to me. And so I'm trying my best to sort of play the devil's advocate game and think, well, if it was going to be doing all the things that brains can do, would it do that? And maybe not. And if so, if it wasn't doing that, how else would it solve that problem? So I'm not against using it. I just think we have to be careful.
You could go the reverse way, right? Instead of saying that brain is following the language, you can say language evolved from the brain. That is, the language, the whole concept comes from, you know, intraneuronal communication, and that same architecture of taking bits and making into bytes and then they're chunking it in different lengths. That architecture turned into verbal language. So if you when you go from the perceptual part of the brain, which is we discussed earlier on, below the roof of the midbrain, if you look at it, all you need is just sharp transitions, which let's call that transition as a bit. And you take 2 bits, put it together into the shortest byte, and let's call that as a syllable. And this intra-bit spacing, if you keep changing, you can get different lengths of syllables, and then you can pack them into also different lengths together and create words of different lengths. That is, you can have a 2-bit byte or a 4-bit byte or a 8-bit byte or something like that. So if you keep on doing that, then you go from this concept of a contrast becoming a syllable, becoming a word, becoming a phrase, and building up. And that is how I think the primordial brain communicates to the cerebral cortex, which is the cognitive portion of it. And in the cognitive portion, we only process syllables.
So
language evolved from the architecture rather than the other way.
This is, I think, what Chomsky seems to be saying, but he says it happened like in a flash, like one suddenly. But again, Chomsky seems to think that that evolution happened all of a sudden to be able to produce language. But
no, I don't think he says that. Anyway, the paper that I sent you.
His idea is that it happened all at once. Because his idea is that there was no proto-language, right? So there's a whole lot of back and forth about that, and very controversial. But what I'm ambivalent about whether you need separate stages for the primitive brain going to the more cognitive brain. But what
you need communication between primitive part and the cognitive part. I'm saying that is where the basic idea of symbol comes.
That's precisely where the anthropomorphization comes in, because it's like as if the primitive brain is just doing its thing and then says things once in a while to the other part.
No, it is constantly recognizing this contrast, which is bits. And if you start chunking bits, you get into bytes immediately, then becomes, you can just create barcodes and you can create words and you can just build it recursively, right?
So here's like a different angle on a similar idea, which is that like some people will say, and I tend to agree, that the purpose of the brain is to control the body. And from that perspective, what is thought? Like some people want to say the purpose of the brain is consciousness, and then what is thought becomes a hard question to ask, because that's sort of the point. But if we keep behavior and movement in the foreground, one way of thinking about movement, which actually maps nicely onto the anatomical perspective, is that thought is virtual movement. And what is virtual? Virtual is a kind of outgrowth of planning. And not just planning, but who said, did someone say simulation? Charlie said simulation. So there are neural correlates that suggest things like look ahead planning involves simulating something in some space. People see this with the place cells also, right? That you see this kind of sequence of firing that corresponds to place cells that they will go to. Interpreting this is very hard, but if you just think about what a person does, and even an animal, sometimes you can see them, the wheels are spinning, what do I do next, right? So there's a type of invariance that comes from needing to do this. Like if you imagine a simple system which basically reacts to all of a certain type of categorical stimulus, then there is no ability to inhibit that behavior. Once you get the ability to inhibit a behavior, then you can say, walk towards the fire instead of running away from it, right? So we develop this inhibitory control, which can override certain ancient associations, right? And then you can ask about the invariance of planning, because now, maybe earlier, your sequencing was very closely tied to what you're immediately about to do. So that getting some activity in a premotor area might be, equivalent to doing it a few seconds later. There may not be that much gap between them. But if it's the case that you now have this copy of what you could be doing, and not just a copy of what you could be doing, but a copy of its consequences in a virtual world, then you start to have this simulation idea. And it's not exactly the same as thinking, as symbolic thinking necessarily, but it relies on a kind of encapsulation of the action, right? Because for me to virtually think about all my movements, I don't necessarily excite the exact same network. I might weakly excite the motor cortex, just enough to, in fact, this is very speculative, but one way I was thinking about this was that embodied cognition could be tied into procedural and episodic memory, which is that when you're doing things, everything that you're perceiving and doing is being mapped to each other and to nodes that correspond to that particular episode. And to get a really robust recollection of those things, as soon as you start to plan for something, like if I'm thinking about moving my arm, I might as well use that signal to sort of flush out all the associations that come with that, which is another way of saying the exact same thing. which is that that's a simulation. So
except simulation happens one bit at a time. It is not like running in someplace and then slowly coming out. Everything is happening in the now. So
it's constantly happening at various time scales.
It is happening at various time scales, but executed finally in the motor system one bit at a time. It has to come down to that, right?
Is a symbol like a unit of simulation? If you're running a simulation, is it a quantized component of that simulation? Is the definition of a mental symbol is a simulation of an action could be a symbol, or something that you're acting upon could be a symbol. So basically that motor behavior, when it's made into the simulation, is defined as the quantized symbols.
Yeah, that's why I was using it as a synonym for both symbol and syllable. Like previously, when I was talking about swimming, when you're swimming and you want to turn around, it's a sequence of commands you have to give, but the elementary command, the lowest level, is one syllable, and you take permutation combinations of syllable, you can create your entire memory.
One way to think about it is that it's chunking, right? And like maybe music is a good example. That initially people are putting a whole lot of effort into just not having both two fingers move at the same time, right? Whereas once you're able to do that, you say, I can do a trill. And then the trill kind of has its own unit to it. But I don't think it's completely hierarchical, because people who are extremely skilled are able to move their attention from a heavily chunked level all the way down to very, very fine motor control. So I don't think it is obligatory for that type of thing to be hierarchical.
The difference I think about it is I can sing a phrase, but I have absolutely no clue what notes I sang. Whereas my wife, being a musician, she can think about it in terms of notes, and she can go play it in a piano or any other instrument. So she can deconvolve it into a symbolic language or a syllabic language. Whereas for me, it is whole chunks, one word full of all those bits. I have memorized it in the sequence. I just dump it as either a dump of my procedural memory or an episodic memory. And it is coming out as a bit stream, but not labeled syllables that have that I have associated a meaning to.
Yeah,
so I'm just like regurgitating. My brain is like a tape recorder. I just recorded it and I'm just dumping it boom, 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 one at a time. But I have no idea what notes I'm singing, right?
Yeah, it's like some people when they're learning a language by immersion, they're not. They're just going to whole phrases might just come out of their mouth, and that's in some sense easier. And it's fun to see little kids do that, right? Where they just utter a complete phrase, and it's pretty clear that they don't know what they
don't know what. Like I have a video of little kids chanting the whole Veda, the mantras, like it's 40,000 words or whatever it is. They can memorize and just completely say it, but I'm not sure they understand anything of what they're saying. 40,000 words.
This relates to, I think I brought this up before, but this issue of realism in art, right? There's a question of how did people get to draw things in a representative way, like perspective and all of that. And if you look at children, how they draw typically, they'll draw not what they see, but what they know. And what is that distinction? So they'll draw a table with all four legs visible. There's a sense in which the facts about the objects are in the front of their attention, and then that is what has access to the motor commands. So what artists need to do is unlearn that very useful thing, like being able to live in the low dimensional space of objects is probably very useful, which is why that's what people do, and that's kind of the natural thing to do. And even people who don't interact with something very often, they'll tend to be all thumbs metaphorically in that space. If they don't cook much, if they don't, whatever it is one doesn't do, you tend to view it in, like, for lack of a better term, a sort of pixelated way. Everything is sort of blocky. And short-circuiting that, well, actually the opposite of that, going the long way, is to work back down to develop the fine control. They're reading a book saying that everyone who can write down their own name has enough motor control to draw. The issue is not motor control in the traditional sense. It's a form of perception. And again, for lack of a better term, it may not be symbolic, but it's something to do with the coarsest categorizations that we have are something like symbols.
Yes.
That's how I see it. Anyway, that's
so the thing that Ram was referring to with the kids learning, reciting Vedas without knowing the meaning, right? That's Daniel Dennett has this really nice phrase for it: competence without comprehension. So that's kind of what we mostly do, and I think that relates back to something that Mac was talking about earlier, which is that most of what we do in our daily life is sort of this competence without comprehension, and then once in a while, the tip of the iceberg thing, kind of like, you know, some symbol comes up, and we either articulate it in terms of words, or we say that I've attended to that symbol or whatnot. But
it becomes famous in Dan Dennett's language, right? He says fame in the brain is a really nice analogy for consciousness, which is that for a period of time, some set of the system becomes more available to the rest of the system, and it also then defines everything that happens to the system from that point on, such that everything must be viewed in the context of that famous subset. That's a really nice idea. It has some limitations as well, but it's like a nice way to frame the problem that has a nicer temporal dimension to me than a lot of the other popular theories of consciousness, with IIT and global neuronal workspaces and things. Just sort of say, if this happens, then you're conscious, not what happens going forward now that you're conscious of that one bit. I like the fame in brain idea for that perspective.
What fascinates me about this, and which I think is not too hard to map onto the global workspace, is that it seems to settle on a notion of potential. So there's a sense in which there's an actualized potential, right? Because the things that I can talk about, like the factual claims I can make about my desk, right? There's a sense in which I am aware, not of the actual sentences that I will eventually say, but the potential for all of them in some sense. So there's like a richness of experience that everyone experiences that we know cannot be collapsed into a small number of sentences. In the same way that and so you can think, it's like a speculation that what you're conscious of is like the subjective counterpart to a set of potentials. Like what you are not conscious of.
So Delegger and Dewhurst have this really nice article I can try and dig up, where they argue that it's got the fame in the brain idea needs to be extended slightly to make sense, which is that not just that you have the potential to be famous, but that you actually probe the famous people. So you actually have to ask, you have to do an interview of the famous people for them to be relevant. This is a lovely idea, right? That as soon as we turn the camera off Trump, all of the problems that the world was facing seem to diminish, right? That we were giving people this voice seems to be the thing that matters. So it's the probed potential that is the subset that really matters for subjective experience. That's the kind of advanced, thought idea.
Yeah, that's perfect, because to make that a physical thing, there's some sort of sense in which there's a scan going on, right? Maybe it's like way faster than because when we feel as though something is stable, that we don't experience any kind of scanning, right? But maybe it's the case that there's a juggling or something cycling on the burner on some time scale, and those things can enter into relations. Whereas something that is in your memory but not currently anywhere near relevant is the opposite of famous in the brain, and it's not on your mind, and therefore it cannot be the cause of me picking up a glass, right?
The other analogy that I quite like, though it's not as popular as well, was from Rodolfo Linas, who is a big thalamocortical researcher, and he had this nice analogy of the vortex. And the idea is sort of like, if you've got a whirlpool nearby you and you're a little water molecule sitting a little bit away from it, there's a sense in which you're not anywhere near likely to get pulled into that vortex. But the closer you move to it, or the closer the vortex moves to you, the more you get pulled in to that vortex and now a part of the vortex. And so the vortex is constantly evolving. And you can almost think of it as like a little attractor running around your brain going, oh, I'm going to take this little bit in now. I'm going to take that bit in now. And so since if you have the vortex idea in your mind, you can then think, well, is there a part of the brain that's likely to be part of the vortex based on where we think the thing's moving or the context is moving? Is there a part of the brain that was just in the vortex and now is in a refractory period and no longer can be part of the next, vortex in the next moment? And so that would take advantage of some of those, the psychological refractory periods and things like that we know are characteristic of our conscious awareness. So it's an interesting idea as well to think of that, right, as like an attractor that's currently kind of defined by the pieces that are representing our conscious awareness. And it's ever changing. I like that idea as well, but I'm not sure it completely captures it either. But it's fun to think about these different analogies and how they can help.
I like that this vortex idea and the dropout thing too.
That's a consolidation of short-term memory to long-term memory can be visualized that way, right?
Yeah, lots of things.
But what I was thinking of is like also the Tononi has this stuff about sleep and like sleep-like states in the waking brain where part of the brain will sort of drop out. And I think they correlated that to in motor cortex with errors. And everyone has experienced that situation of like you're going to say something that you've said many times or a word you've used 10,000 times and it just vanishes from your mind. And as an energetic thing, like something that was firing away, and then the local interneuron said, "Okay, you've had enough. Like, take it easy." Did anyone else want to say anything? I feel like the symbol concept thing is very rich, and most of us don't explicitly have a definition of what a symbol is. I don't really, but I just have this vague notion that comes mostly from mathematics. Any suggestions for what to talk about next week? I have a few ideas, but I know Charlie, you said you had some ideas for papers you wanted to talk about.
Yeah, I want to talk about Peirce's semiotics and Deacon's spin on it, but that will probably have to wait until like the semester is over, like maybe beginning of June or something.
Yeah, semiotics. Let's wait on it.
Yeah, that's a very after the main discussion, but
well, it's building off of off this whole information thing.
Yeah.
I was going to go essentially through Deacon's chapters on information where he talks about Shannon information, but then brings up I guess the Peircean notion of information through.
Somebody recommended Ruth Millikan and biosemiotics. I will, by the time we talk about this, maybe I'll do a dive into biosemiotics also. But for next week, there's a paper that I'm planning to present to my lab, so it will be two birds with one stone if I talk to you guys about it. It's this Paul Chisek paper on phylogenetics.
Oh, I'd love to speak about that. Yeah, I'd be happy to
fantastic paper.
Yeah, that would be great.
So, Johan, I think for that, I think we should do that in relation to the structural model from your lab. You only briefly talked about it before. I think we should synthesize both the Chisek work and your lab Helen's structural model and see how we can synthesize it.
Yeah, because Chisek doesn't talk about the cortex much because he's talking about all this other stuff.
I know. I think that's why it's very important because they're kind of at the evolutionary scale in some sense. So it'll be good to see how we can synthesize the function and the natural history and the structure.
Sounds good. So next week we are putting on our Darwinian hats and getting into some intense, really detailed developmental biology and evolutionary biology.
Johan, Paul's a friend of mine. Do you want me to try and get him or someone from his lab to join, or do you want to do it separate?
Oh, get Paul?
I can try. I mean, he loves a good chat, but I don't know if he stays up as late as you guys.
Feel free to email him.
I'll ask him if anyone from his lab wants to come join.
Yeah. I met him once years ago, but he probably won't remember me.
Johan, another thing that we can tie with that, because we're talking about evolutionary stuff, is that I know Mac wouldn't be very happy, but it's the David People, Asif Ghazanfar, and the John Krakauer, the behavior paper. Remember that the brain as behavior.
Brains need behavior.
It's a very easy paper to summarize. Yeah.
It's a good paper too. I mean, yeah.
I think tying that ethology and the kind of story that Zizek wants, and also the structure that you have in your lab, I think that'll be very interesting just to try to discuss all that.
Yeah. Yeah,
I'm not friends with John Krakauer, so I'm not going to email him.
Okay, time to stop recording, right?